This is Gary Greenberg from Edge-3D. Edge-3D is producing a line of innovative 3D imaging tools for research, industry, and biomedicine. The big question is, why 3D? The most important thing about microscopes is you're acquiring information about the object you're investigating. 3D provides more information, and thus you get increased productivity and improved diagnosis. Take a look at something that we're all familiar with, the difference between a 2D X-ray and a 3D CAT scan of the heart. About 30 years ago or 20 years ago, all that one could see is an X-ray, as you see on the left side of this image. But now with today's 3D technology, the amount of information gained by stacking and being able to see in 3 dimensions has led to huge breakthroughs in biomedicine. The same is happening now in microscopes. The problem with microscopes is that it's old 2D technology and it has very, very shallow depth of field. So here's a little bit of an electronic circuit board. If you look with a regular microscope, you're going to see the foreground, and as you focus through, you focus down, you begin to see different parts of this object. But you don't see the whole thing at once. So what the Edge microscope does is it takes all these pictures and together puts them all into focus, just as you see here. The foreground and the background is totally in focus. This overcomes the problem of depth of field and you get a full focus image. Now, one of the things you can do with the Edge-3D microscope is see the 3D as a rotating object. So it produces rotational films, and that allows you to see the 3D without any special glasses. However, if you would like to see the 3D in stereo, most people can easily get red cyan glasses. If you put on your red cyan glasses for a minute, you can now see really the third dimension of what this object is. It adds a lot more information. You can take your red 3D glasses off now. So the same thing is true in biomedicine, and even more so. Here's an example of a brain cell. A regular microscope, you see the foreground and the background is out of focus. So with the Edge microscope, you take a series of images as you focus from the top of this section. This is a 120 micron section, and you focus through the entire or most of the nerve cell. And as you focus through, it puts it all together into one image that's fully in focus. Now you have a tremendous amount of information, all compressed in focus, 120 microns thick. Then, if you want to see it in a rotation movie, which can be shown on the internet or at a conference, you can see the 3D that way. But even more interesting is to be able to use the red-green glasses and be able to really see the 3D. Now, if you're using one of the 3D computers that comes with the Edge 3D system, you'd be using active glasses, so it wouldn't be red and green, and the image would even be more dramatic. Edge is also making a macroscope, a low-power version of its microscope. On the macroscope, you can either put on, as you see on the left-hand panel, something like a digital SLR camera with a macro lens, so you can get close-up information and inspection all in focus. It automatically focuses in the same way the Edge microscope does. And on the right side, you could hook up the USB 3 camera. Video camera is another way of addressing the information, again with a macro lens. So what is the competition? The instruments from the major manufacturers sell from 100,000 to more than 1 million. Kayence and Hyrox have 3D microscopes that sell from 50 to 150. And Edge, the macroscope, is coming in at about 15,000, and the microscope somewhere between 25 and 45,000, depending on all the features you might want to have on it. So we're very competitive. We have real-time 3D imaging, which other products do not have. We have greater value for price, and it's super easy to set up and to use. So who needs 3D? The two main areas are research and industry. In research, probably neurobiology is, I would say, the most important application, and this should be probably the first place to be able to really use this in a large scale. The brain and the nervous system is intrinsically a three-dimensional problem. The same is true of cancer biopsies and developmental biology. And there's a lot of action today in 3D cell culture, 3D tissue culture, and plant biology and marine biology and so forth. They're all good applications. In industry, whether you're making an aircraft carrier or a refrigerator, most industries use inspection systems, general quality control, things like failure analysis, corrosion analysis. These are very good applications for the 3D Edge-3D microscope. So I want to give you a little tour of what the images look like in 3D. So if you put on your 3D glasses now, I want to show you the added information that you get. Here is a single Purkinje cell taken from the cerebellum of the brain. You can see the cell body just here. And these are all the dendrites. There's 1,000 dendrites or so. And these are all the connections you made with other cells. And then one output through this little axon here. And you can see the whole thing in 3D very, very, very nicely and very easily. You could not see this with a regular microscope. Here is a capillary bed. Here's a blood vessel here in the brain. These are capillaries. And you can really easily see the three-dimensional structure of these capillaries. So if you're studying vascular biology, this is an important application, an important tool. Here is a flat piece of paper. But a flat piece of paper, if you look very close up with a microscope, is anything but flat. This is about the size of a period, this entire thing here. And you can see that from the laser printer, those are the toner particles that are scattered on top of the fiber in the paper. Now in document analysis and forensic science, people often look at documents and how they're signed. The interesting thing about when you sign a document, you actually put a permanent little crease into the paper. So you can see here that the vertical signature or the vertical line was done first, and this line was done second because you can see in 3D there's a trough there, and that has been maintained, and you can actually see it in 3D. If you close one eye, you wouldn't be able to have that information. Another great application is geology. This is a meteorite from the moon. And you can see the surface is really, even though it was a cut flat surface, you can see there's lots of important three-dimensional information. And as you go and get closer, you begin to see the sorts of fractures and three-dimensional information that geologists are looking for. These are micrometeorites from outer space. They were once falling stars. And you can see some of them are actually hollow inside. And if we look closer at that with a little high-power lens, you can actually see right inside of this. This is just a tiny, tiny little grain of sand, about 0.2 of a millimeter. Here's a grain of sand from the moon, a tiny grain of sand from the moon that's about 4 billion years old. And you can clearly see in 3D the incredible structure of the crystals that make up this grain of sand. Here's another grain of sand from the moon. Many grains of sand from the moon have these apparent holes in the middle that were caused by micrometeorite bombardments, little tiny grains of dust going 120 or about 20,000 miles an hour, impacting the sand on the moon and creating these little circular, what are called ring agglutinates. You can remove your glasses now. So many people ask, how do you publish 3D information? Well, the answer is you publish it the same way that confocal microscope users publish their information. Generally, they publish a compressed 2D reconstruction of the three-dimensional stack that they acquire. Another way is to publish stereo pair images. You can publish left-right stereo pair images. This is often done in chemistry, especially where you're looking at the three-dimensional structure of molecules. You can also publish using cyan glasses, the cyan red glasses as an anaglyphs, as we just showed you. Or you can show rotational videos and post them online. So here's an example of how you might take one thing. So here is a regular two-dimensional version of a grain of sand from the moon. Here it is all in focus, so this is the way you would publish it. Or you could publish it like this with the red-green glasses so people could appreciate the three-dimensional structure. Or you could post it online as a rotating three-dimensional image. The three-dimensional panfocal software is powerful and easy to use. One simple interface runs the entire microscope, the camera, and so forth. So as you look at this microscope here, you can see that these lights here, those run the reflected lights, and you can place them wherever you want. So here's the reflected lights. This bank of lights here controls the transmitted lights that come through the condenser lens into the specimen. Rather than having one light here, there's two lights here. There's a left eye light and a right eye light. And that allows you to get real-time 3D images. So when you click real-time 3D, these left and right lights go on and off quickly, and it produces a real-time 3D image here on the screen. Here is all the stage movement here. So let me just click here. So the lights were there. Here is where the stage is focused. So by moving this slider up and down, you can focus the stage up and down. Or by using these arrows, you can set the size of the movement you want. This tells you where the stage is. And then this area here tells you how to stack the images. So you just say the number of stacks you want, where to start, where to end, and then just say, take a stack. So it's very, very simple to use. In the next part, in part 2 of this, I'd like to do a live demonstration using two types of specimens, a transmitted light biomedical application and a reflected light industry application. Thank you very much. Now I would like to give you a live demonstration of how the Edge panfocal 3D software controls the Edge research microscope. So let's just click here on the Edge icon, and that will load the software. So this one software screen controls all the aspects of the microscope, including the camera, the focus, the lights, and the processing of the images. So right now you can see that the camera status is ready. It's turned on. These are the reflected lights on the left, the transmitted lights on the right. So right now we have a brain section. I'm going to use transmitted lights to look through this brain section. You can see some neurons there. And one of the first things you'll always want to do is make sure that you're focused. I'm just closing down the field stop to make sure that our condenser is centered and focused. So we're about in the middle. This is about 120 micron thick section through the brain. Now normally people would take 5 micron sections. So we're taking sections that are more than 20 times thicker and seeing it all at once and in 3D. So this is a single optical section through the middle of this. So I'm going to tell it right now to go through the entire 120 microns, and you're going to watch it take a stack. I just click take a stack, and it's going to go to the 0 position. So that's the very top of this specimen. And as you can see, it's focusing through. And every 7 microns, it's taking 18 pictures at different levels. And then what it's going to do, it's going to put all those pictures together, reconstruct them, and now they're all there, all in 3D. Or I should say that's a 2D reconstruction of all of those images there. Now I'm going to click here, do the same thing that I'm going to click high res. And when it does it in high res, it's going to do the same thing, but what it's going to do is every single layer in this stack will be a 20 megapixel image. So the resolution will be extremely good, and it'll allow you to do some very interesting movies and 3D stuff. So let me just show you right here a little more about the program. So here's how we use the focus. This was a sliding bar, and as you move this up and down, it controls the focus of the microscope. Over here, you can focus the microscope using up and down arrows. You can use the arrows on your keyboard or your mouse as well by clicking here. And by setting this number, every time you click, it will take you those many microns. In this case, it's 10 microns. So right now, you can see this is the current focus position. You can see that this number is moving as it's taking that stack. So right now, we're at 77 microns out of the 120 microns that it's taking images of. Here's where we told it how to take the deep focus. We said every 7 microns, take a step. starting at 0, going to end focus. This is a 120 micron thick section. So there were 18 pictures. And all we did was you click take a stack, and that's what it's doing right now. You can see it moving through the specimen. Now once it's collected all the images, these 20 megapixel images, and then it will begin to reconstruct them into a fully focused, to begin with, a fully focused 2D compression of these images. So right now it's working on it. So it'll come up with a view in 2D, which is a reconstruction, a compression of all the 3D images put together. Well, we can see that in many different ways by clicking here. These are the various viewing options. So you can see it as a rotational movie. You can see it in stereo 3D if you have a 3D computer, which the Microscope comes with. Or you can see it in anaglyph 3D, which I'll be able to show you because you've got the red and green glasses, and that allows you to see it in 3D. You can generate a color depth map to see where the information, how deep the information is in microns. You can create a grayscale anaglyph, which gives you a black and white version of what you're looking at in case there's some colors that interfere with the red and green image. So right now it's done a first pass, and there we go. There's all the images now fully in focus. And now we're going to click on anaglyph, color anaglyph. So if you get out your red and green glasses, click on anaglyph, sorry. Get out your red, it's now creating the anaglyph. And if you put your red and green glasses, now you'll really be able to see not only all of them that are in focus through this 120 microns, but exactly where they are in 3D. So I'm going to click this larger screen icon here. Now you'll see it larger. So there you go. Now you see all of the microns that were, all of the neurons that were in those 120 micron thick specimen. But you see them in the foreground, you see what are in the background. You get a very accurate information about what is actually there. And as you look with the glasses, you can look at one individual neuron and see how it interacts or relates or does not relate to neighboring neurons. I'm going to go back to the control panel here and back to the compressed view. And now what I want to do is show you a very different kind of specimen. I'm going to turn off these lights. And what I want to now do is put up a very different kind of specimen, geological type of specimen. In this case, this is some sand from the volcanic sand from the Galapagos Islands, showing various types of volcanic minerals that come off of this particular island. So right now I'm going to go to live view, and now I put different specimen in there. Now I'm going to put on the reflected lights. There's the reflected lights coming on, and there's some sand. I'm going to lower the stage because this is a thicker specimen. As I lower the stage, you'll see the individual grains of volcanic mineral come into view. I'll move the stage around a little bit and find a view to show you when I stack the images what it will look like. So here's an interesting little view here. So what I'm going to do is the first thing is I lower the stage so that I come to the top of the specimen. So right now we're lowering the stage, and I'm already past the top of the specimen, so I'm going to come back up to the top of the specimen, which is right about there. This little grain, that's the top right there. I'm going to set that as 0. That's the current start position. But I'm going to raise the stage till I get deeper into these sand grains. So I'm raising the stage. You're seeing the focus go through, and I'm going to probably set that right about there. Now I'm in the background here, and those are in focus, so I'm going to set that as the current end position. So that was 400 and almost 500 micrometers. We're using a low power, using a 4x lens right now, so we're going to look at 40. We're going to look at 40 micron steps, and now what we're going to do, we're going to name it Galapagos. And now we just say take a stack. And right now we're set on we're set on the 20 megapixel high resolution version of this particular, in other words, we're clicked on high res right now. So each picture in the stack will be a 20 megapixel picture. As it's collecting these, you can see that we can output the files in various ways. So I typed in the word Galapagos. That's going to give the name to every picture that I take as long as this same slide is in the field of view. It's going to save it in a directory called Edge-3D, and it's going to name them sequentially starting with 1, and you can set any number here you want. Now, it'll automatically save as a JPEG and a TIFF. The 2D reconstructed version automatically gets saved. But if you want to save other forms of the data, such as a stereo image, a JPS file, or an anaglyph, meaning a red-green version of stereo, or a grayscale anaglyph, you can check any of these boxes, and the ones that you check, it'll automatically save those file formats without having to go to the File Save As command. So you can save the left-right stereo images, you can save a color depth map, a grayscale depth map that tells you which each feature is in the Z dimension. You can save it as a 3D model. So right now it's focused down at the bottom of the specimen, and it's just now processing the first round of processing, and then it'll go to the second round of processing. So it'll take about 15 more seconds here. What I'm going to be able to show you is that there we go. So here's the all in focus, and now if I click this button that says 3D model, now we can actually move around the specimen and tilt it and look at different angles using a 3D model. Or we can do a rotational film. So if we make a little film here of this, I'm going to say create film. And what this is going to do, you have control over the step size, that is how many angles on the clock angle that you're looking at this rotational film from, and how many pixels in displacement, that is how extreme you want the oblique view to be when you look at the movie. So right now we've picked 9 and 15, which are good sort of default numbers. And then in a few seconds it'll have created the movie. It's put it all together. Now it's putting it into an AVI file. And you say want to view it, and you say yes. And we push enter. And now we can see, I'm going to just enlarge this here. Now we see the 3D by virtue of motion parallax. This gives you a very interesting way of seeing what's in the foreground, what's in the background, and distinguishing really what's there. So I'm going to close that out and close this out. So if I want to save, I'll say no. I'll go back to live view. Now I'm going to turn off our lights. And that ends this particular demonstration of the Edge-3D confocal software. Thank you very much.